welcome to this problem walkthrough. Today, we'll explore an interesting algorithmic challenge titled Construct the Lexicographically Largest Valid Sequence. We'll break the problem down step by step, analyze the approaches, and discuss the complexity. Let's get started. In this problem, you are tasked with constructing a sequence based on a given integer n, where 1 equals n equals 20. The sequence must have a length of 2 n1, and it needs to satisfy 3 important conditions. First, every integer from 1 to n must appear exactly twice in the sequence. Second, for each integer I, the distance between its two occurrences must be exactly I. This means that if I appears at positions p and q, then the absolute difference between p and q must equal I. Lastly, among all valid sequences that satisfy these conditions, you must return the lexicographically largest one. If there are multiple such sequences, any of them is an acceptable answer. Let's look at a few examples to better understand what this means. In the first example, when n is 3, the sequence has a length of 2 3, 1 equals 5. The output is 3, 1, 2, 3, 2, 1. Here's why this sequence is valid. The number 3 appears at indices 0 and 3, and the distance between these positions is 3, which satisfies the condition. Similarly, the number 2 appears at indices 2 and 4, with a distance of 2, and the number 1 appears at indices 1 and 5, with a distance of 1. Therefore, all the conditions are met. Additionally, this sequence is the lexicographically largest valid sequence for n equals 3. To see why, note that the number 3 was placed first, making it the largest possible starting number. Now consider the second example, where n is 5. The sequence has a length of 2 5, 1 equals 9, and the given output is 5, 4, 3, 5, 2, 4, 3, 1, 2, 1. Let's verify that this sequence satisfies the conditions. The number 5 appears at indices 0 and 4, and the distance is 5, which is correct. The number 4 appears at indices 1 and 5, with a distance of 4. Similarly, the numbers 3, 2, and 1 all appear at their respective positions with distances of 3, 2, and 1. Since every number from 1 to 5 appears exactly twice and the distances are correct, the sequence is valid. Furthermore, it is lexicographically the largest sequence because the largest numbers, like 5 and 4, are placed in the earliest possible positions while still maintaining validity. In the third example, when n is 2, the sequence has a length of 2 2, 1 equals 3. The output is 2, 1, 2, 1. Let's confirm its validity. The number 2 occurs at indices 0 and 2, and the distance between these positions is 2, as required. The number 1 occurs at indices 1 and 3, with a distance of 1. All conditions are satisfied, and this is the lexicographically largest sequence for n equals 2. To summarize, the problem requires careful placement of numbers to ensure that all conditions are met while prioritizing lexicographical order. The constraints, such as n being up to 20, mean we need an efficient approach to construct the sequence, especially for the largest cases. Lastly, edge cases like n equals 1 and n equals 20 emphasize the importance of considering both the smallest and largest inputs to ensure correctness and performance. When tackling this problem, one of the first approaches to consider is a brute force method. The intuition here is straightforward, since each number from 1 to n must appear exactly twice in the sequence, with specific gaps between their occurrences. We could try generating all possible permutations of the sequence and check which one satisfies the constraints. To clarify, for any number x, its two occurrences must be placed exactly x indices apart. This means that for x to fit at indices I and I plus x, both indices must be within bounds and unoccupied. While this approach is simple to conceptualize and implement, it is computationally expensive. The time complexity grows factorially as the size of the sequence increases. For example, constructing permutations for larger values of n, such as 20, becomes completely infeasible. This trade-off makes the brute force approach impractical beyond small cases, despite its simplicity. Recognizing this limitation, we turn to more efficient methods like backtracking. Now, backtracking offers a more strategic alternative to brute force. Instead of blindly generating all permutations, this method incrementally builds the sequence while ensuring the constraints are met at each step. This allows us to prune invalid sequences early, avoiding unnecessary computations. The process begins with an empty sequence of size 2 n1. From there, we attempt to place the largest number, n, at valid positions first. Once n is placed, we recursively move to the next largest number, n1, and so on. At each step, we check that placing a number x at indices I and I plus x satisfies the constraints before proceeding. This recursive strategy ensures that only valid sequences are explored. While backtracking is still exponential in the worst case, its ability to prune invalid paths makes it significantly faster than brute force. Another potential approach is iterative construction, where we attempt to build the sequence dynamically using a stack or similar structure, placing numbers from n down to 1. However, this method is generally less intuitive to implement and offers no clear performance advantage over recursive backtracking. After evaluating the different approaches, we chose the backtracking method as our strategy for solving this problem. The main reason is its efficiency in pruning invalid sequences early, which reduces the overall search space. Once the constraints of the problem are clearly understood, backtracking becomes an intuitive way to directly construct the sequence. Importantly, by starting with the largest number and working downward, this method naturally ensures that the sequence is lexicographically largest. A key insight here is that placing the largest numbers first guarantees that the overall sequence remains optimal. Another breakthrough was recognizing that backtracking avoids the combinatorial explosion of brute force by systematically ensuring constraints are met at every step. Comparing the three approaches, brute force is simple but infeasible for larger values of n, while iterative construction is viable but more cumbersome to implement and debug. Backtracking strikes the perfect balance between simplicity and efficiency, making it the most practical choice for this problem. Finally, let's analyze the complexity of our chosen backtracking approach. In the worst case, the time complexity is O(n), since we may explore all permutations in the worst-case scenario. However, this is significantly reduced in practice due to the pruning of invalid sequences, which avoids unnecessary computations. As for space complexity, the primary cost comes from the recursion stack, which requires O(n) space. This is because, at any given time, the depth of the recursion corresponds to the number of numbers we are attempting to place in the sequence. Overall, while backtracking is computationally intensive for very large inputs, its efficiency and practicality make it the best approach for constructing the lexicographically largest valid sequence within the given constraints. To tackle the problem of constructing the lexicographically largest valid sequence, we first need to understand its constraints. We are given a number n, and we must construct a sequence of length 2 n1 where each number from 1 to n appears exactly twice. The two occurrences of a number x must be separated by exactly x other elements. If this is not achievable, we return an empty list. For example, consider the case where n equals 3. A valid partial sequence like 3, 1, underscore, 3, underscore, ensures that the two 3s are separated by exactly 3 elements, satisfying one of the constraints. To solve this, we use backtracking. Backtracking is a systematic way to explore all potential placements of numbers while ensuring that the constraints are satisfied. If a conflict arises, we backtrack to try a different placement. This approach is particularly well suited for problems like this where the solution space must be explored incrementally and methodically. We begin by initializing the sequence. The sequence is represented as an array of size 2 n1, where all slots are initially set to -1 to indicate they are empty. Next, we define a helper function called backtrack, which is a recursive function responsible for attempting to fill the sequence starting from a given index. The strategy starts with the largest number, n, and tries to place it in valid positions within the sequence. This ensures that the numbers with the largest separation constraints are handled first, reducing the complexity of subsequent placements. For any number x, we iterate through the sequence to find an index I where both the current position I and the position I plus x plus 1 are empty. If such a position exists, we place the number x in those two slots. This placement step is critical because it ensures that the separation constraint 4x is satisfied before moving forward. If the placement fails, we remove the number and backtrack to explore alternative configurations. Once the recursive backtracking function is implemented, we need to handle its outputs. If the backtracking process successfully places all numbers from n down to 1 into the sequence, we return the completed sequence as the result. However, if it becomes impossible to place a number due to conflicts with the constraints, the function will eventually backtrack completely and return an empty list, indicating that no valid sequence can be constructed. This process highlights the importance of systematically exploring placements while avoiding unnecessary recursive calls by pruning invalid states. By starting with the largest number, we optimize the search space and minimize the likelihood of running into conflicts later. Additionally, edge cases such as n equals 1 are straightforward to handle, as the sequence is simply 1. The key insights here are the effectiveness of backtracking and navigating through possible placements and how constraint checking prevents futile computations, making the algorithm efficient in practice. When analyzing the space and time complexity of this approach, we see that the worst-case time complexity is factorial in nature, specifically O(n). Since we may need to explore all permutations of placements for the numbers. However, in practice, pruning significantly reduces the number of recursive calls. The space complexity is O(n), driven by the recursive stack depth, which is proportional to n, and the sequence array itself, which has a fixed size of 2*(n)(1). To solidify our understanding, let's consider an example where n equals 3. Initially, the sequence is empty, -1, -1, -1, -1, -1. We first place 3 at positions 0 and 4, resulting in 3, -1, -1, -1, 3. Next, we place 2 at positions 1 and 3, yielding 3, 2, -1, 2, 3. Finally, we position 1 at the remaining slots 2 and 3, completing the sequence as 3, 2, 1, 2, 3. This example demonstrates how backtracking systematically builds a valid sequence while adhering to constraints. The final implementation in Python begins by defining the construct_sequence function. Inside this function, we initialize the sequence array with -1 to represent empty slots. The backtrack function is defined recursively to fill the sequence starting with the largest number down to 1. At each step, we identify valid positions for the current number based on the constraints, place the number if possible, and recursively attempt to place the next smaller number. If a conflict arises, the function backtracks by removing the number and exploring other options. Once all numbers are successfully placed, the sequence is returned. If no valid configuration is found after exhausting all possibilities, an empty list is returned. This implementation efficiently combines recursive exploration with constraint checking, making it a powerful solution for the problem. Here, we begin the implementation of the function construct_distanced sequence inside the solution class. The goal is to construct a sequence of integers that satisfies the problem's constraints. First, we create a list called sequence with a size of 2*(n)(1), initialized to zeros. This list will store the resulting sequence. We also define another list, used, with n+1 Boolean elements, all set to false, to keep track of which numbers have already been placed in the sequence. Next, we define a helper function named backtrack that will be used to explore all possible placements of numbers recursively. The function takes an argument index, which represents the current position in the sequence we're trying to fill. If the index reaches the end of the sequence, meaning all positions are filled, we return true to indicate a valid sequence has been found. If the current position is already filled, we skip it by calling backtrack with the next index. The main logic begins with a loop that iterates over numbers from n down to 1. This ensures we try placing the largest numbers first, which helps construct the sequence in lexicographical order. For each number, we check if it has already been used. If it has, we simply continue to the next number. If the number is 1, it only occupies one position in the sequence. We place it at the current index, mark it as used, and recursively call backtrack to attempt filling the rest of the sequence. If this attempt is unsuccessful, we backtrack by resetting the position and marking the number as unused. When the number is greater than 1, we need to check if it can occupy two specific positions in the sequence, the current index and the position at index plus number. If the position at index plus number is within bounds and unoccupied, we proceed to place the number at both positions. Then, we mark it as used and call the backtrack function recursively to continue filling the sequence. If the recursive call returns true, it means we've successfully constructed a valid sequence, so we return true as well. However, if the attempt fails, we backtrack by resetting both positions to 0 and marking the number as unused, effectively undoing the placement. Finally, if none of the numbers can be placed at the current index, we return false to signal that the current path does not lead to a valid sequence. After defining the backtrack function, we invoke it with the starting index of 0 to kick off the recursion. Once the recursion completes, we return the sequence list as the result. This implementation ensures that every number is placed in a way that satisfies the problem's constraints, while also building the sequence in lexicographical order by prioritizing larger numbers first. Here, we start by defining the structure of our solution. The construct distanced sequence method takes an integer n as input, which determines the size of our sequence. We create an array sequence of size 2 n 1 to hold the result, and a Boolean array used to keep track of which numbers from 1 to n have already been placed in the sequence. The main logic is implemented using a helper method called backtrack. This backtracking function will attempt to recursively fill the sequence array. If we successfully fill all positions, we return the sequence, otherwise, we return an empty array, though this fallback case shouldn't occur with valid inputs. The backtrack function begins by checking if the current index has reached the end of the sequence array. If so, it means we have successfully constructed the sequence. If the current position is already occupied, we skip it and move to the next index. This ensures that we only focus on empty positions during the filling process. Now, the backtracking logic continues by iterating through numbers from n down to 1. This ensures that we prioritize placing larger numbers first, as our goal is to construct the lexicographically largest sequence. If a number is already marked as used, we simply skip it. For the number 1, we handle it as a special case. Since it only occupies one position in the sequence, we place it at the current index, mark it as used, and recursively attempt to fill the remaining sequence. If the recursion succeeds, we return true. Otherwise, we backtrack by resetting the position and marking the number as unused. For numbers greater than 1, we attempt to place the number at the current index and also at the position index plus number, as each number occupies these two positions in the sequence. Before placing the number, we ensure that the second position is within bounds and is currently empty. If these conditions are met, we mark both positions, set the number as used, and proceed recursively. If the recursive call fails, we reset both positions and unmark the number, effectively undoing the placement and exploring other possibilities. Finally, the helper function returns false if no valid configuration is found for the current state of the sequence. This signals the need to backtrack and try alternative placements in earlier recursive calls. With this approach, we systematically explore all possible configurations of the sequence, ensuring that we construct the lexicographically largest valid sequence. The backtrack function is the heart of this solution, leveraging recursion and backtracking to handle the complexity of the problem while maintaining the constraints of the sequence. Once the sequence is successfully filled, the result is returned to the main method, completing the implementation. To solve this problem, we need to construct a sequence of length 2 n 1, which in this example equals 5. The sequence must be both valid and the lexicographically largest. A valid sequence ensures that for each number k from 1 to n, if k equals 1, it occupies one position, and if k greater than 1, it occupies two positions spaced exactly k indices apart. Starting with the initial state, the sequence is an array of zeros, and the used array keeps track of which numbers have been placed. The recursive process begins at index equals 0. Here, we try placing the largest unused number, which is 3. We check if positions 0 and 3 are available, and since they are, we place 3 in those positions, update the sequence to 3, 0, 0, 3, 0, and mark 3 as used in the used array. Next, the recursive call proceeds to index equals 1. Here, we attempt to place number equals 2. However, position 3 is already occupied, so we skip 2 and try number equals 1 instead. Since 1 only occupies one position, we place it at index equals 1. This updates the sequence to 3, 1, 0, 3, 0, and we mark 1 as used in the used array. Moving to index equals 2, we now try placing number equals 2 again. Positions 2 and 4 are available, so we successfully place 2 in these positions, resulting in the sequence 3, 1, 2, 3, 2. The used array is updated to reflect that 2 has been placed. At index equals 3, we skip it since it's already filled with 3, and at index equals 4, we skip it as well because it's filled with 2. Finally, we reach index equals 5, which is beyond the sequence length. At this point, we've reached the base case because all positions in the sequence are filled, and the sequence is valid. The recursive process concludes, and the resulting sequence is 3, 1, 2, 3, 2. Now, let's consider another example where n equals 4. Here, the sequence length is 2 n 1 equals 7. The initial state begins with a sequence of 7 zeros in a used array indicating that no numbers have been placed yet. The recursive process starts at index equals 0, where we attempt to place the largest unused number, 4. Positions 0 and 4 are available, so we place 4 in these positions. This updates the sequence to 4, 0, 0, 0, 4, 0, 0, and marks 4 as used. Continuing to index equals 1, we try placing number equals 3. Position 4 is already occupied, so we skip 3 and move to number equals 2. Positions 1 and 3 are available, so we place 2 in these positions. The sequence becomes 4, 2, 0, 2, 4, 0, 0, and 2 is marked as used. Now, at index equals 2, we attempt to place number equals 3. Positions 2 and 5 are available, so we place 3 in these positions. This updates the sequence to 4, 2, 3, 2, 4, 3, 0, and 3 is marked as used. Finally, at index equals 6, the only remaining number is 1, which occupies one position. We place 1 at index equals 6, resulting in the final sequence 4, 2, 3, 2, 4, 3, 1. At this point, all indices are filled, and the sequence is valid. The recursive process concludes, and the output for this example is 4, 2, 3, 2, 4, 3, 1. This demonstrates how the algorithm constructs the lexicographically largest valid sequence by attempting to place the largest available number at each step while adhering to the validity constraints. The time complexity of this algorithm is primarily determined by its backtracking approach. The goal is to construct a valid sequence by exploring all possible placements for numbers from n to 1 within the array. To do this, the algorithm recursively traverses the sequence, which has a size of 2 n 1. At each position, it attempts to place a number and checks if the placement is valid. Validity checks involve ensuring that the current position and the calculated index for the second placement are unoccupied. These checks operate in constant time, or O1. However, in the worst-case scenario, the algorithm may need to explore all permutations of numbers from n to 1, which results in a factorial growth of possibilities, approximately n. This factorial growth is what dominates the time complexity in the worst case. The backtracking process relies on recursive exploration, which can be visualized as a tree structure. Here, the branching factor corresponds to the number of numbers that can be placed at each step, which is up to n, and the depth of the tree is limited by the length of the sequence, or 2 n 1. While the theoretical maximum number of recursive calls corresponds to exploring all n permutations, in practice, the algorithm prunes invalid placements early, significantly reducing the effective search space. For example, placements that violate the constraints, such as already filled indices, are skipped immediately. This pruning prevents unnecessary computations and improves efficiency. Despite this optimization, the worst-case bound remains O(n), as the algorithm must still consider all valid permutations when the input is highly constrained. In the best-case scenario, a solution may be found early, requiring fewer recursive calls, but the O(n) worst-case complexity is the dominant consideration. The space complexity of the algorithm is primarily influenced by the recursive call stack and the auxiliary data structures used. The recursion depth is determined by the length of the sequence, which is at most 2 n 1. This means the space required for the call stack is proportional to n, or O(n). Additionally, the algorithm uses two key auxiliary arrays. The first is the sequence array, which keeps track of the current state of the sequence during the backtracking process. This array has a size of 2 n 1, contributing another O(n) space. The second is the used array, which tracks which numbers have already been placed in the sequence. This array has a size of n+1, which is also O(n). When we combine the space required for the call stack and these auxiliary arrays, the overall space complexity of the algorithm is O(n). To put the efficiency of this backtracking approach into perspective, let's compare it to a brute force method. A naive solution would involve generating all possible sequences of length 2*(n)(1) and then verifying which ones satisfy the constraints of the problem. This would result in a staggering time complexity of O(2*(n)(1), as it explores every possible permutation with repetition. In contrast, the backtracking approach narrows the search space significantly. By pruning invalid placements early and skipping already used numbers, the algorithm avoids many unnecessary computations. This reduces the problem to exploring only valid permutations, with a worst-case time complexity of O(n). Additionally, the space complexity remains O(n) due to the efficient use of the recursion stack and auxiliary arrays. Overall, backtracking provides a dramatic improvement over the brute force method by leveraging constraint-based pruning to achieve much greater efficiency. When solving this problem, there are several common mistakes to watch out for. First, not handling constraints properly can lead to invalid solutions. For example, if you place the number 3 at indices 0 and 2, it violates the rule that the gap between duplicates must match the number itself, as the gap here is only 2 instead of 3. Another frequent issue is relying on inefficient approaches, like brute force, which generates all permutations without pruning invalid candidates. This is especially problematic for larger values of n and can result in timeouts. Additionally, incorrect index calculations are a typical pitfall. Remember that indices are zero-based, so a gap of 2 means the position should be I and I plus 3, not I plus 2. Overlooking edge cases, such as n equals 1 or n equals 2, can also cause runtime errors or incorrect outputs, so ensure to handle these explicitly. Lastly, failing to mark numbers as used after placing them can lead to duplicate placements in the sequence, which breaks the problem's constraints. Being mindful of these mistakes will help you avoid many common pitfalls. Now, let's focus on insights that are especially relevant for interviews. The key takeaway here is that this problem tests your ability to manage state and recur sufficiently, making a strong understanding of backtracking principles critical. One optimization strategy is to place the largest numbers first, as they have stricter placement requirements. Solving for them early simplifies the problem and reduces the search space significantly. It's also important to test your solution against a range of scenarios, including edge cases like n equals 1 and n equals 2, as well as larger inputs such as n equals 10, to ensure both correctness and efficiency. When discussing your solution in an interview, prioritize clear communication. Explain your thought process, how you plan to handle constraints, the techniques you use to optimize the solution, and how you test edge cases. Additionally, related problems like LeetCode 46, 47, 51, and 526 can help you build a deeper understanding of backtracking and constraint satisfaction. For example, LeetCode 46 and 47 focus on permutations, while LeetCode 51 and 526 involve arranging numbers under specific constraints, making them highly relevant practice problems. There are also alternative approaches to consider. Backtracking with constraints is a common strategy. This involves starting with the largest number and recursively placing others, ensuring constraints are met early. By doing so, you effectively reduce the search space, though the approach remains exponential in the worst case. A trade-off of this method is that while it's efficient compared to brute force, it requires careful implementation to avoid redundant states. Another option is a greedy approach combined with validation. Here, you attempt to place numbers in a greedy manner and then validate the sequence. While this method can be faster, it's less flexible than backtracking and might fail for certain edge cases. Lastly, dynamic programming offers another alternative. By representing partially filled sequences as DP states, you can potentially achieve faster solutions for larger values of n. However, this approach is complex, requiring significant memory and careful implementation, which makes it harder to code and debug effectively. Each of these methods has its strengths and trade-offs, so choose the one that best suits the problem constraints and your familiarity with the technique. Thank you for watching. We reviewed the key aspects of the problem and learned how backtracking can help construct lexicographically valid sequences. Remember to practice similar problems to strengthen your skills. Like, subscribe, and stay tuned for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!